Welcome to the 2017 International Science Education Conference. My name is Dr. Nicole Simon from Nassau Community College, Long Island, New York. This is a presentation on iconic representation as an assessment of impact on critical thinking. Digital natives. Computer game technology is poised to make a significant impact on the way our youngsters will learn. Our youngsters are digital natives, immersed in digital technologies, especially computer games. They expect to utilize these technologies in learning contexts. This expectation and our response as educators may change classroom practice and inform curriculum developments. This research was conducted at a two-year community college as part of the State University of New York Consortium. We looked at several factors that are critical to science education, which include critical thinking and cognitive load. We did this looking at iconic representations, which is the use of imagery in scientific concepts. It's a key component of improving critical thinking skills, and we look to maintain optimal levels of cognitive load within higher education STEM learners. And we did this because laboratory experiences are vital components of science education, and rote traditional lab experiments are currently not addressing inquiry nor linking with educational technologies. Critical thinking includes both deep and surface level learning, and we're looking to see students transition from surface level to deep level learning while optimizing cognitive load, which is the ability to use working memory and prior knowledge to enhance learning and memory retention. We use instructional approaches that are based on active discovery and problem-based learning, which is a key component in digital games and very commonplace in today's educational forum. We use opportunities to alternatively assess learning and evaluate comprehension in a digital learning environment, and we looked at this from a theoretical and an empirical research perspective. We were hoping to have our students learn in a format that they're more comfortable with. By using educational games for assessment, not only were we able to measure previously outlined learning objectives and goals, but to measure their cognitive load abilities throughout these scenarios. We did this with dynamic visualization, which includes animations, and it entails intricate processes that have been found beneficial in the composition of laboratory schemata. Educational technology, in addition to instructional system designs, often presume that iconic representations are advantageous when employing kinetic rather than static graphics. Iconic representations include anything that is visual, and by visual we mean it could be static, it could be kinetic, it could include animations and graphics, including bold text and not text. We use the cognitive theory of multimedia learning by Mayer, where multimedia presentation includes words that are directed to our ears, pictures that are directed to our eyes, and this form of sensory memory allows both selected words and selected images to be transmitted into your brain through sounds and images. This all works in our working memory to allow our brains to organize words and organize images. When we organize words, we use the verbal model for mental representation, and when we use the images, we use pictorial models for visual mental representation. Both of these are integrated, and at the interface of where they're integrated, long-term memory takes hold. Long-term memory includes prior knowledge. So what we're looking for cognitive theory and cognitive load is using this working memory, relying on prior knowledge, building our long-term memory, and optimizing this integration point without overtaxing student learning. In order to do this, students need to transition from surface level learning, where they learn material, to deeper level learning, where they're relying on prior knowledge, and this builds critical thinking skills. Our research study determined how the use of iconic representation in our virtual learning environments and how we manipulated these parameters for complexity of learning scenarios. We yielded an increase in cognitive load specifically for inexperienced learners, those students who either lacked the science background needed or the computer background needed. Our data revealed the inclusion of iconic representation can enhance the learning process in those inexperienced learners. And again, this was accomplished by measuring critical thinking skills and cognitive load among learners participants in a two-year community college in New York. We also found to a lesser degree that experienced learners, those students understanding the science or understanding the computer background previously to entering the course, did yield an increase in both cognitive load and critical thinking, but to a lesser degree. We use a classic physics experiment, the force table experiment, describing the relationship between vectors and vector analysis. In the next two figures, I'm going to show you the difference between icons for vector components and the use of animation without iconic representation. A distinction exists between iconic and symbolic representation that's based upon taxonomic representation that will amplify or increase the accuracy and the generalization of the information that's shown. This is figure 1 that shows the force table experiment with icons, the iconic representation. Notice in the upper right-hand corner, you have a pictorial example of traditional laboratory experiment. The lower right-hand corner shows your masses, both in pictorial and in color-coded text. On the upper left-hand corner, you have, again, those masses, and you have different color vectors, and you can see both the masses pictorially and written out in text, and the different colors. This allows students to learn in a multimedia format. Whereas the force table experiment without icons, there's no prior learning, so there's no picture of your traditional lab experiment. There's no pictorial example of your masses. You're again missing those color-coded vectors. Just to show you that difference again. Very much color-coded. Helps the students keep track of which vector is which mass they're using. Here, everything's in one color. So you can imagine students trying to differentiate between the two, having less text and less pictures. Our results show that the critical thinking skills that were assessed for students exposed to iconic representation compared to those students with no treatment, that repeated measures indicated that the icons had some effect on the learning process. It built student knowledge, it allowed them to break from surface learning to deeper learning, and it also showed that the critical thinking skills were consistent with the two main subscales we looked at, deeper learning, and surface learning. It also showed that learners in the treatment group, our iconic representation, had higher levels of critical thinking skills than those students who did not. And you can see this in a positive comparison with our deep level learning. The pre-treatment students had a lower level of deeper knowledge. They were more at the surface level, and our post-treatment showed a much higher level of deeper knowledge by using those critical thinking skills and relying on cognitive load. Thank you.